looking forward to your presentation. Thank you.
Thank you so much for the introduction. So yes, my name is Hande and I'm currently a postdoc at Texas A&M University. My advisor is Professor Ibrahim Karaman. And today I will talk about how we can use a material, which is very interesting material, shape memory alloys, in next generation transportation structures as structural health monitoring elements. This particular alloy is very interesting because it can recover large amounts of deformation. So this is a property of shape memory alloys, which basically they can recover large amounts of deformation compared to a conventional stainless steel. For example, conventional stainless steel, you can deform up to 0.2%. However, shape memory materials, you can get recoverable deformation up to 10%. So this property makes these alloys very attractive for transportation structures. However, and besides these properties, SMAs, shape memory alloys, can provide recentering and great energy absorption capabilities. However, currently available shape memory alloy, which is, some of you might know, nickel titanium or nitinol, is very expensive because of its raw material cost, and plus this material is very hard to machine. So because of these reasons, nickel titanium is not suitable for structural applications. So what we do in this work is to introduce a low-cost alternative of these SMAs, which is iron-based shape memory alloys. And what we want to do is to use and incorporate these materials into structures. And plus, there's this additional property of iron-based SMAs, which they can show magnetization change during deformation. So we want to use this property to monitor deformations in the structure. So we want to use this material as a health monitoring elements in the structures. Like I said, what we want to do is to develop low-cost, multifunctional, high-strength, and self-sensing wires, braided cables, and large diameter bars, because in structural applications, most of the time, common materials are cables or large diameter rods. So we want to scale up iron-based SMAs. And like I said, we want to demonstrate the self-assessing capability of iron SMAs using this magnetization change. And in conventional nickel titanium, again, you cannot get this magnetization change, and therefore that is not suitable for structural health monitoring applications. So before I start, I just want to quickly explain how SMAs work. So shape memory alloys, like I said, can recover large amount of deformation, and this is due to superelasticity. So this superelasticity is an elastic response of a material to an applied stress, and it happens by a phase transformation from two solid phases. It's a solid to solid phase transformation. So the material transforms from austenite to martensite. So when you release the load, the material goes back to its original state. And there are lots of different iron-based SMAs, but for this project, we selected iron manganese aluminum nickel SMA, and the reason is because this material in this graph here on the left, it shows the superelastic stress levels versus temperature. So superelastic stress levels corresponds to the stress at which this material transforms. Here you can see iron, nickel, cobalt, aluminum, tantalum, boron, or copper, aluminum, manganese, or nickel, titanium alloys. But our composition here, which is shown in the red line, is iron manganese aluminum nickel alloy. And as you can see, as you increase the temperature, the critical stress for superelastic transformation does not increase as much. And this is critical, especially for civil engineering application or transportation applications, especially in the structures in the extreme environments, because once you build your material, you don't want the property of your material to change due to different temperatures. And this graph shows iron SMAs are actually higher, has higher strength and strain levels compared to the nickel, titanium, and copper and manganese SMAs. However, to get a superelastic response from an iron-based SMAs, you need three things. So the first thing, which is extremely important, is the grain size. So in this graph on the top, what you see is a microstructure of a material, and these little areas we call grains. So what you want to do is you want to increase the grain size of the material through heat treatments, abnormal grain growth heat treatments. So if you have small grain size alloy, you don't get that superelastic response that I showed you earlier, which is typical to SMAs. However, if you increase the grain size of an alloy such that the grain size is higher than the smallest dimension of the component, so this is important. So you want your grain size to be higher than the smallest dimension of the component. It can be bars or wires. Then you start to see that superelastic response. So it's extremely important that you manipulate the microstructure and obtain correct microstructure. Also, these materials are very anisotropic. So that means that if the orientation of the grains are different, you can get different response from the material. So if your grains are oriented 1 to 3 direction, you get this nice superelastic response. In 1, 0, 0 direction, you get more hysteretic response. And the last one is, after you grow your grains, what you want is you want to strengthen your material, and you achieve this by inducing these nano-precipitates in the material by low temperature aging. So in my talk, I'm going to talk about how we can develop iron-based SMA wires and then switch to cables and bars. And throughout our experiments, we use different experimental techniques. We use Hasse extrusion, we use microscopy or EBSD to look at the grain orientation. We use furnaces to do our heat treatments. To measure the magnetization change, we used a squid. And this is here the cable setup that actually we built with my undergrads in our lab to fabricate the iron-based SMA cables. And again, XRD for texture measurements. So let's look at how wires work. So if you want to make an iron-based SMA wire, what you want to do is this here is this processing techniques that I showed in the left graph. What we did is we had to extrude our material, then we annealed it, and then we did wire drawing at room temperature. And this part here is where we induce the grain growth. So what we did here is we repeatedly heated up and cooled down the material from room temperature to 1200 degrees C. And when you repeat this heat treatment a couple times, you get grain growth. So after that, you need to solution heat treat your material, and to strengthen your material, you need to do aging heat treatments. We did, in this case, 200 degrees C for different amount of time. And after that grain growth, we were able to increase the grain size up to 40 millimeter in 0.5 millimeter wires. However, but before I talk about the larger diameters, of course, this wire is very small for civil engineering applications. But to get a material property, to get the insight on the material properties, we looked at the effect of nanoprecipitates on the superelastic response. So this graph shows basically that you can manipulate the supercritical superelastic stress levels, so the stress at which your material transforms, by changing the aging heat treatment. So if you can change from 1 hour to 24 hours, and you can control this stress levels. Then after we developed the small diameter wires, we developed the first iron-based SMA cable that shows superelasticity in the literature using this iron manganese and nickel cables. And here you can see on the right, there's an SEM graph of this cable. We used 7 different cables and braided them together, and we built this, we fabricated this using the setup that I showed you earlier. And again, like I said, the microstructure is very important. So we apply heat treatments in these materials, and this graph shows the microstructure of a cable. And you can see the grain size, our grain size is higher than the smallest dimension of the component. And when you test the material, we were able to obtain superelastic response. And after that, we worked on 2 millimeter diameter bars and 5 millimeter diameter bars. Again, we applied this abnormal grain growth heat treatments into these materials and repeated 5 times from room temperature to 1200 degrees C, and we were able to grow the grains in these bars too. But again, this is very important. This heat treatment is very important because you need to optimize the heat treatment specific to your material. As the dimension of the component increases, so the heating cooling parameters or the microstructure will change. So therefore, you need to optimize the heat treatments as you scale up the material. And we also developed another alloy. So we added some titanium into iron manganese and nickel. And in this material, you can get much faster grain growth rates if you apply these heat treatment procedures. So in this case, in iron manganese and nickel titanium, we changed our heat treatment parameters to 900 C to 1200 C. So we cycle our material between these 2 temperatures. And when you do that 3 times, you can get single crystal in 4 millimeter diameter bars. And here you can see this is samples that we heat treated. And when we measure using XRD or EBSD, you can measure in 2 different techniques. We saw that this material is single crystal. But in the future, what we want, of course, is much larger diameter bars, 8 millimeter to 10 millimeter rods. So in iron manganese aluminum nickel and iron manganese aluminum nickel titanium, we fabricated these bars. So what you do, you take this S-cast billet and you hot extrude it at 900 degrees C. And when you do that, you can get 8 to 10 millimeter bars. And after that, you need to apply those heat treatments again, which are very critical. And in iron manganese and nickel titanium 8 millimeter bar, we, after repeating 3 times, after cycling this material 3 times between 900 C and 1200 degrees C, you can get large grains. We didn't observe any grain boundaries after this heat treatments. Still, we are continuing this work. Let's look at the self-assisting capabilities of iron-based SMAs. So like I said, these materials show a magnetization change during this phase transformation. So what we did, we wanted to take advantage of this property and build self-sensing sensors out of these materials. So this is our setup, this is our sensor, and you place a magnet, and this is the wire that we measured. So what we did is we continuously recorded the magnetization change, magnetic signal change during this superelastic test. So when, like I said, the austenite and the martensite that I talked about earlier has a different magnetization level. So for example, you load your material and you transform to martensite, and when you unload, you go back to austenite. However, if you load, in this case, 5 or 6% strain, you get some irrecoverable strain. So this irrecoverable strain means that remnant martensite in your material. So because this martensite has different magnetization levels, you can see that the magnetic flux changes after 4 or 5% in iron manganese aluminum nickel wire. So here we show that this change using this in-situ experiments. And again, we established a direct correlation between this remnant deformation, which is the volume fraction of the martensite in your material, with the magnetization change. So using this property, you can use these materials as self-sensing elements in civil engineering applications. And again, we tested iron manganese iron nickel titanium specimens. After abnormal grain growth, we didn't observe any grain boundaries. So that means that we have single crystals because we measure the gauge length in XRD. And we tested our sample. Here is how our sample looks like. We designed this in SolidWorks, and this is our setup. And we measure the magnetic change during superelastic response. And again, so the blue line represents the stress. The red line here represents the magnetic signal. So as this material deforms, you get a change in the magnetic signal. And here you can see actually in this image is that these lines, that it represents martensite. So the single crystal alloy transformed to martensite as shown in these images. And again, we also established a direct correlation between remnant deformation and magnetization change in iron manganese and nickel titanium alloys. And of course, during this whole process, I worked with amazing undergrads. So this is me and Jessica. We were doing these heat treatments. She helped me a lot, and Albert's work helped me to develop this wire testing setup together with Peter. So thank you to all of them. And during the course of our research, we not only did scientific research, but we also wanted to disseminate our results to next generation leaders. So we attended the departmental seminars. I gave a course lecture to undergrads and explained how these new materials can be used in civil engineering applications. These are my conclusions. So we developed oligocrystalline superelastic iron-based SMAs, wires, cables, and large diameter bars. And we fabricated iron SMAs for the first time, which is very attractive for civil engineering applications. And the magnetic
semi-empirical, and you were like, now in a true or false question, if it says semi-empirical, it's true. Now if it says mechanical.
No, but by the way, I don't know how to make true and false question anyway.
Sorry about that.
So yeah, and magnetic response, we established the magnetization change during superelasticity, which can be used to monitor, detect stresses and strains in the next generation structures. Thank you for listening to me. If you have any questions, I'm more than happy to answer.
Thank you very much. And I think we have a few questions on the chat, and maybe Dr. Holzkan, if you can read it, or I can read them for you.
Yeah, I cannot see chat, I think, here.
Okay, so I can read them. One of them is, what is the cost of shape memory alloy? Actually, it's very general, so I will read the three questions. What is the cost? Any DOT in US has used it. Can you replace steel?
Yes, so the cost of SMA actually ranges between, like, it's dependent on the composition. Like I said, the traditional ones, if you go to the market right now, the currently available one is nickel titanium. And the nickel titanium is very expensive for civil engineering applications. Specifically, I don't know on top of my head how much is the unit cost for nickel titanium, but you can easily find, the Fort Wayne Metal, the Alloy, these are the companies that produce these alloys. But these materials, because they're expensive, they are mostly used in aerospace applications. But in iron-based SMA, our material is much more cheaper than iron, manganese, aluminum, nickel, because we have iron, we don't have titanium in the material, in our alloy. So that significantly reduces the cost. And plus, the processing of iron, manganese, aluminum, nickel is very easy compared to nickel titanium, because it has iron in it. It's very similar to the normal conventional stainless steel. So that means that the industries, they already know how to process stainless steel, can easily switch to iron-based SMA. So in that sense, it is very advantageous. Currently, I don't think any of the DOT in the US is using SMAs. And that is also because so far nobody could scale up nickel titanium to large scale applications. Although I think there is one demonstration of nickel titanium in the bridges for energy absorption capabilities. They showed that demonstration. I don't remember the name of the bridge, but if you can leave me your email, I can send it to you after this talk.
So, Dr. Oskan, the chat is very active, more than any other speakers. Some mentioned about the bridges in Seattle using, I think it's nickel titanium.
Yes. Bridges in Seattle uses nickel titanium, correct, yes. But again, nickel titanium, that is also very good for energy absorption capabilities. So you can use nickel titanium. But again, you need to watch for the cost. And plus, nickel titanium doesn't show any magnetization change. So if you want to use SMAs for structural health monitoring, you cannot use nickel titanium. But you can use it for recentering capabilities because it can recover large amount of deformation.
They have other questions about the resistance against environmental effects, or if they decompose with time.
So okay, so this is actually a good question. What resistance again? Environmental effects. So in iron-based SMAs, one concern is the corrosion. So because these materials are newly developed, although iron-based SMA research started since 1970s, the main breakthrough achieved at 2010, so it's fairly new, and this material is still under development. So one of the challenges is the corrosion. Corrosion properties can be improved if you add chromium into this material. So if you add chromium into iron, manganese, aluminum, nickel, you can improve corrosion properties significantly. So that's one alternative. That can, yes.
The other question was about the fatigue concern.
Yes, fatigue concern. So again, fatigue concern of this SMAs, in terms of high cycle fatigue, this iron manganese aluminum nickel doesn't perform very well compared to nickel titanium. However, low cycle fatigue of iron manganese aluminum nickel alloys are good. So again, it depends on your application. So if you want to use this material for structural health monitoring or energy absorption during earthquakes or any hurricanes, these adverse effects, you can, iron-based SMAs are suitable for that. But one can add chromium, but it will increase cost for high cycle fatigue response. They will be similar to any.
Yeah.
Yeah, but yes, you can add chromium, or you can, I don't know, coat your material. I am not, the corrosion properties is not my research area, but there are other groups that study the corrosion properties of iron manganese iron nickel SMAs. But
great. I think again, the most popular session, a lot of interesting questions, and obviously it's a very attractive topic. So thank you for an excellent presentation. And if you have questions with Dr. Oskan, you can continue on the chat, or you can reach out to her.
Yeah, my email I will write down in the chat. If anybody has any questions, they can send me emails and I can try to answer them.